All right, so we're going to start with electron dot formulas, and phosphorus has 5 electron dots. Each of the fluorines have 7. And the way I've taught you to put the dots around here, I should do it that way, I guess, is you put 1 electron on each of the 4 sides, or if you have to stop at 3, you stop at 3. But you keep going and then start pairing up until you've used up all the dots that you need in that valence level. Okay? So we're going to put 1, 2, 3, 4, then pair up 5, 6, and 7 to get 7 dots around the fluorine. Okay? So those are electron dot formulas. And then we can share electrons to get arrange the electrons so that each element has access to 8 electrons. 8 electrons makes these elements, these particular elements, more stable in their valence level. So we're going to share electrons until we get all of them so they have 8, and that will do it. Then we're going to go to the Lewis dot formula, where we have the shared electrons are squeezed up between the element symbols, and then we put our electron dots around that. And then we'll go to the Lewis formula, where we replace shared pairs and only shared pairs with lines. So only this set of electrons and this set of electrons and this set of electrons are shared. All the others we have to leave as dots. So that's actually showing the bonds between elements there. And then we want to find a 3-dimensional arrangement. The first one of those 3-dimensional arrangements is going to be called an electron pair shape. And for that, then we go back to our Lewis dot formula and count the sets of electrons around the central atom. Now, sets can be electrons. Sets of electrons can be 2 electrons or 4 or 6. In this earlier example up here, this set between 2 atoms is made of 6, and that makes up a set. Any number of electrons between 2 atoms is a set. Any lone pair is a set. So in this case, we have 4 sets, 1 lone pair and 3 sets that are pairs themselves, shared pairs. And the 3-dimensional arrangement that gets 4 sets of electrons as far apart as possible in this valence shell electron pair repulsion theory is a tetrahedral. And we're going to have one going up like that. One of these goes over here to 109.5 degrees. And this is where, Tevin, you were asking about the triangles. This is where triangles have to come in, because now we have to have a set of electrons that are sort of swinging out from the paper toward you. Okay? And then a set of electrons that are swinging back behind the paper away from us. And we're going to put our sets of electrons around that, 4 sets. Okay? And we call that a tetrahedral electron pair shape. From that, then we're going to do a modified electron pair shape, where we're going to only replace those pairs or sets of electrons that are actually shared. We have 3 of them that are shared, so I'm going to replace 3 sets on this drawing. But I'm going to still leave the set that isn't paired. So here's our phosphorus, and this set I'm going to leave right here unpaired, but I'm going to put fluorines on this set over here, and a fluorine on this set down here, and a fluorine on this set right here. So I'm going to replace these 3 sets with 3 fluorines, because that's what I have up here. The 3 fluorines shared with 3 sets of electrons. Then the last drawing I'm going to do here is where I take that lone pair off, but I'm not going to change the shape. The shape has to stay the same without that lone pair on there. That's the only thing that doesn't. The only thing that changes is we remove any lone pairs. So we're going to put a fluorine down here, and a fluorine coming out toward you and kind of down, and a fluorine going back behind and kind of down. Okay. All right, so this is still a tetrahedral. It's a tetrahedral modified electron pair shape. This is a molecular shape now, because we no longer have any lone pairs on here. Once you get to that point where there are no more lone pairs on the drawing, that's a molecular shape. But this is not tetrahedral, because we don't have that 4th arm up here. Almost. Trigonal pyramidal. Yeah, it's trigonal pyramidal. Okay, it's like a 3-sided pyramid, sort of a shallow 3-sided pyramid. Okay, if I were to connect all the dots or the fluorines down here, we'd have a shape that looks something like this, which is a sort of a shallow 3-sided pyramid. You see that? Okay. All right. So now this is an uneven arrangement. But for polar bonds, we have to have two conditions, the uneven arrangement and polar bonds. So we still have to figure out whether the bonds are polar. Okay? What we know right now is this is uneven. And the bonds are not different. These are all the same bonds. So we don't have to worry about whether there are different kinds of bonds making it uneven. Okay? We have the same kind of bonds all the way around. They're unevenly spaced. We just need to know if they're polar or not. So for that, then we have to figure out the electronegativity difference. So fluorine has an electronegativity of 3.89. Electronegativity for fluorine, I'm sorry, I said 8.9, it's 9.8. And then the electronegativity for phosphorus is 2.19. Okay. And so the difference is 3.98 minus 2.19, and that's 1.79. So that's why I thought you were asking the question about ionic a while ago, because this is 1.79. That's the electronegativity difference for a phosphorus to fluorine bond. Okay? Well, if we go back here to that chart that I gave you to use for this stuff, that falls in that ionic range, wouldn't it? Okay? So, if that's all you have to go with, you'd have to say this was an ionic bond. This was it wasn't a molecule at all. It's ionically bonded.
So, like, how polar bonds and hydrogen.
Say what now?
You have to have two of those to be polar?
You have to have both conditions, polar bonds and an uneven arrangement. This is an uneven arrangement, but based on what you know so far, you would say, well, that's just ionic. We're not even going to call that polar. And in fact, it's probably somewhere between ionic and polar, because, again, there are factors beyond what we study in this class that we don't consider here. Okay? Yeah.
Okay. When you're drawing the molecular shape,
Mm-hmm.
how do you only use like the shared pair, the little items? Why do you put the long pair?
Well, when we're doing the three-dimensional shapes, we do use a line to show the direction of the lone pair.
The lone pair is.
Well, here's the modified electron pair shape. There's a lone pair right there. We don't use lines for lone pairs when we're doing Lewis formulas. We do use lines when we're trying to figure out this molecular shape. Okay, so these three steps are part of the process of figuring out a molecular shape. Okay? We don't actually go beyond this much in high school chemistry, but in chemistry later, let's say you want to do something in medicine, these are things you got to be able to do. You got to be able to figure out. The fact that this is the shape it has impacts the shape of the molecule, and much larger molecules get impacted by that shape. All right? And that makes the shape of things like proteins in your body take the shape they take. This interaction and these interplay between the lone pairs and the bonds, those all affect those shapes, and they're very, very important. Even something as simple as breathing is affected by this sort of thing. Okay? Breathing takes oxygen from the air, filters it into your bloodstream. It changes the pH of your blood. The pH of your blood goes up in your lungs. And so the hemoglobin, the heme molecule in your hemoglobin, changes shape in your lungs because of the change in pH. And that has to do with these kind of concepts. So that change in shape then allows CO2 to leave the hemoglobin and oxygen to flow into the hemoglobin. Okay, the heme molecule. Then the heme molecule travels down, hemoglobin with the heme molecule in it, travels through your bloodstream down to the ends of those blood vessels where the pH increases. The pH is increasing because of the CO2 that your muscles are giving off. I'm sorry, decreases. CO2 causes it to decrease. And the change of that heme molecule changes again, allowing that oxygen that's trapped in the lungs to flow out and the CO2 to flow in. And that whole process just continues on and on. And this is kind of a beginning place for understanding first organic chemistry in college and then biochemistry, so that if you're going to do something in medicine, you have a grasp of what's going on and why it's going on. Okay? So we're just sort of beginning to lay a foundation for your understanding of that later on. Okay? So, but the lone pair, even though we don't shorten the molecule, what we care about when we get to things like that level is the shape of these bonds, not where the lone pair is so much. Those lone pairs do have an impact, but not in the shape of the molecule. Yes?
Did you say this was polar? No,
Well, you would have to say this, we have to call this ionic, because that's what the bonds show right here. This electronegativity difference shows that. Okay? In fact, it's probably, in reality, it's probably somewhere in between ionic and polar, but that's for stuff that we don't teach at the high school level. Has to do with the size of the atoms and things like that, how tightly fluorine actually holds on in its size, the shielding effect on fluorine affects all that. So this would, while in reality this is probably really more a polar molecule, you would have to say at this point in time that it's ionic. Okay? It has an uneven arrangement, but nevertheless it's ionic because the bonds are showing ionic. Does that make sense?
not really.
Okay. So it confuses you that what you have to predict is different from reality? Is that what's confusing you? Okay. I mean, I could not tell you that. I could just say you'd call that ionic and not tell you about the other stuff. But then I don't want you to get to college and say, well, Mr. Tedder said. I want you to know that there are other things you're going to learn about later. Remember, when you started this class, when you were in physical science, we talked about you had 18 electrons on some circles in that around the nucleus of an atom. But we said, when we got here, that those are all in sublevels. So we split them up into S sublevels, which have 2 electrons, and P sublevels, which have 6. So we learned more about the structure of the atom in here than you learned in physical science. Remember that? Okay, well, this is the same sort of thing. We're telling it to you here one way. When you get to another level, they're going to tell you it's a little bit something different. Maybe I shouldn't tell you it's going to be something different. But you just have to use the tools that I give you. And the tools I give you, you should be able to figure it out. This is unevenly arranged, and these are polar bonds. Does that make sense? I mean, not polar bonds, ionic bonds. Is that clear? That clear enough for you? Because your tools tell you that. Okay? You don't have all that other information that impacts what's really going on. You just have to go with the tools I give you. Is that fair enough?
I guess so.
Okay, it's a place to start. Okay? Because it's far too much to pile on you to show you all these other things that go into it. Okay? Do you understand that greater than 1.7 you would call an ionic bond?
Mm-hmm.
Okay? So you call that ionic. All right? But you say it's also unevenly arranged over here. All right? But you still say this is an ionic bond, or this is an ionic substance because of the ionic bond. Because that's what your electronegativity difference calculation told you. You okay with that? All right. Now this we can actually go about grading this one. Okay. So let's see. We have to have an unevenly arranged drawing. So they have to come up with a drawing like this to get to, what did we give this for yesterday? 3 points. Okay. If they came up with a trigonal pyramidal shape, they'll get 3 points for that. If they say that it's unevenly arranged, that's going to be 3 points. If they have the math to show the calculations, that's 3 points. Okay. Now, in terms of them explaining what the result is, they can either say it's ionic or they can claim it's polar. I'll accept either one of those. Okay. I'll accept either ionic or polar for the molecule. And if it's ionic, it would be a molecule, but if it's polar, they can say it's a molecule. Okay? But they have to have an explanation that makes sense. That's the other 3 points. All right? Their explanation needs to be, if they're saying it's polar, a polar molecule, they need to say that they have an uneven arrangement and polar bonds. Or I guess they could say it's ionic bonds, I suppose. Or they could just simply say, if they're saying it's ionic, they can say that the range is in ionic range. So we have an ionic compound. All right, so they just all I'm asking you to do is to have a reasonable justification, a reasonable explanation. Okay? All right, let's go to the last one. Now, the last one won't pose any confusion. Let me go ahead and change this over. Capture. Stop.